Hi guys, this is Ms. Hargrave and your 2.3 notes. We're starting with accuracy and precision. Off to the side, I would suggest that you define those terms. Here I've got 3 bullseyes or dartboards, and the X's would be where the darts would hit. Okay, so with accuracy and precision, we're looking at the closeness to something. So accuracy would be the closeness of all of our attempts or our darts to get to the center where our bullseye is. Okay, precision would be the closeness of all of my darts. Okay, all my attempts. Maybe I was very wrong, but all my attempts were about the same. They were all very wrong, but all very close to each other. And so these would be precise here in the middle and out here because they're very close to each other. And so we're going to look at these terms down here. I have 4 terms: precise and accurate, precise but not accurate, accurate but not precise, and neither accurate nor precise. So looking at our dartboards, here I've got my 3 darts. They're very close, but they are not close to the bullseye, to this dot in the middle. Okay, so they are precise but not accurate. And so we would want to look for that one right here. This one, we can write our answer to that next to the side would be an A, which I have under the sticky note. Looking at B, they're all very close to being correct, okay, or at least the accepted answer, and they're all close together, so they're precise and accurate, the first 2, so I can go ahead and reveal those. And then for the next one, in dartboard C, my darts hit very far from each other and also far from being correct. So with our last 2 options, is this accurate but not precise, or are they not accurate and not precise? My answer would be the very bottom one. C is there. So percent error, you have your experimental value, what you've done in a lab, subtracted what you should have got, okay, or maybe what you started with. You want to divide the difference between those by what you should have got, your accepted value, and multiply it by 100 to get a percent. Okay, and we're going to use this formula to determine for our mixture lab how much salt should we have. Well, if I started with 10 grams, I should end up with 10 grams, but maybe I only measured out 9 grams. Where did that 1 gram go? And then we can talk about some of that. So here I have practice problem C. I'm on page 43. I'm trying to figure out the percent error. If in lab I get 17.7 grams and I should have got 21.2, how much was I wrong by? So then we take what I got in lab, my experimental, I subtract my accepted, what I should have got. Divide it by the accepted, multiply by 100, and you see I get a negative number. That is fine. Most of the times, if you are not at 100%, you're below 100%. That's negative. And so I missed 100% by 17%. So it's not great, but it's not good either. You want to be around 10% off. If you go above 100, you'll have a positive number. And again, you want to be right at 100, as close as you can. Okay? Go ahead and do number 2 in your notes in the reflection side for me. Significant figures. These are really important for our class, making sure that our answers are written correctly. So I would copy the rules, which are in figure 3.3 on page 45. I'm going to fly through these. You can read and then ask me questions if you need to later. So here are 4 rules in green. Purple are our examples. So zeros in between non-zeros are significant. Here I have 40.7. If I take out that 0, that becomes 4.7, a very different number. So that 0 is significant. And that means there are 3 significant figures, sig figs, in this answer. 1, 2, 3. Okay. Number 2, zeros in front of all non-zeros are not significant. They're holding places. Down at the very bottom, I have a note in blue that says, when you're in doubt, just convert it to scientific notation. That scientific notation will help you figure out what is significant and what is not. Is it just holding a place? And we'll practice scientific notation in just a minute. And so here you can see these are just holding places. They're not actually important. The numbers behind it, they're non-zeros, so they are significant. So I have 5 sig figs, and in this one I only have 1. Rule 3, Zeros at the end of a number and to the right of the decimal are significant. That means I have measured those exactly. The only uncertainty would be the very last digit that could be estimated, but I have measured to that decimal point. So 85.00, there are 4 significant figures. These 2 zeros are important. And then the last rule, zeros at the end of a number, but to the left of the decimal, may or may not be significant. And I have those that may or may not explained right here. If the zero has not been measured or estimated, it's a placeholder, and that's not significant. So down here in purple, I have 2,000 meters. Is that exact? If I'm saying, it's about 2,000 meters from here, I haven't measured that. I'm just guessing. So those zeros are not significant. I only have one significant figure, the 2, the non-zero. My second part, a decimal after zeros show zeros are significant. And so here I have 2,000 with a decimal afterwards. That means exactly 2,000 meters from here, you will find XYZ. And so each one of those zeros are significant. So with the 2, I have 4 sig figs, okay? All right, and then there's the note, when in doubt, convert to scientific notation. Rounding. Rounding depends on the type of math you're doing, so we're going to start with addition or subtraction. Your answer has to have the same number of digits to the right of the decimal point with the fewest digits. Basically, you can only be as accurate as your least precise device or measurement tool. And so that's why it's the fewest digits. So our question, look at it. Here's our 2 numbers. I have them added and subtracted. It doesn't matter. Just examples. Which has the fewest numbers after the decimal? Here is 0.1 and here is 0.03. So 1 significant figure versus 2. 1 is the smallest. So my answer has to have 1 decimal point, not the 2. So you would want to circle these ones. These ones are not correct. Okay, we round to 1 decimal point. Multiplying or dividing with decimals. So here our answer can have no more significant figures than there are in the measurement with the fewest significant figures. What that means, I have here. Look at your answers. Which one has the fewest number of sig figs? Significant figures. So I have 3.05, 8.47. There are 3 in each, right? Because that 0 in between the 3 and the 5, that is significant. So I divide these 2, and I get this long number, but there are 3 sig figs in each. So my answer has to be 3. So 0.360. The 0 will not make this round up. So it stays, okay? Do number 1 and 4 from page 48 in your notes, just to practice, and we'll go over it in class. I also have one extra note at the bottom. Conversion factors are exact, okay? Exactly 100 centimeters are in 1 meter. So both of those zeros are significant, okay? And it would be 3 significant figures for that. And they can be written either way, 100 centimeters on top or on bottom. It just depends what we're trying to find, and we'll practice that later. All right, scientific notation. So it's written as a whole number between 1 and 9, could be a decimal, times 10 to the nth power, or a whole number, that's our exponent. So to find m, you want to move the decimal points until you get 1 non-zero. We don't want 2. I don't want 11.9. I want 1.19. And so then I have my example in green. I have 0.00012. I move the decimal point until I get 1.2. This is not completed. We complete it here in step 2. So then I have to find n, which means I need to count how many times did I move the decimal point. If I move it left, then my exponent is positive. If I move it right, my exponent is negative. So when I moved it over, this is to the right, so that means it's going to be negative 1, 2, 3, 4. So my answer should be 1.2 times 10 to the negative 4, and I always have to include my units, millimeters. All right, so now if we are adding or subtracting with scientific notation, you can only do this if your exponent, the end factor, is the same for both or all of your adding or subtracting numbers. If they're not, then you have to adjust them to be the same. And so here I have two numbers, 1 to the 10 to the 4th power and 1 10 to the 3rd power. So I do an example adding both of these together, 10 to the 4th power, 10 to the 3rd. So when I do that, it's just a matter of adjusting the decimals. This was 4.2 times 10 to the 4th, but because I moved the decimal to the right, that's negative. It takes one away from my exponent. So it was 4, and now it's 3. And then the same with this. It was 7.9 times 10 to the 3rd, but I moved the decimal to the left, which is positive, and so it becomes 0.79 to 10 times 10 to the 4th power, okay? Then you get your answer, and it needs to be rounded to the number with the fewest significant figures. So I look at them, and I have 2 significant figures in each of them, so my answer should also have 2. Make sure you keep your units the same. When multiplying, the m factors are multiplied, and then the exponents are multiplied separately. And so here you have your example. I have a number to the 6th power and a number to the -2 power, and these are called micrometers. So I put them into my problem, and then I separate out the m's and the n's. These two are multiplied, and you get 37.133. These two are then added. So 6 plus -2 is a 4. And then because I have micrometers times micrometers, my micrometers are squared. I have 2 significant figures because 7.1 is the smallest. So my answer also has to be 2 significant figures. The decimal points can't do anything to round up to 7, so they just get cut off. And there's our answer. Dividing with scientific notation, the m factors are divided, and then the exponents are subtracted, denominator from the numerator. So I write out my problem. I have 5.44 divided by 8.1 times 10 to the 7 subtract 4th power. And because I have grams divided by moles, my units are grams per mole. I get a long number to the 3rd power, but then I need to convert this or adjust it to 2 significant figures because 8.1, there are only 2 significant figures. So I also want to move that decimal point over, and I get 6.2 times 10 to the 2 grams per mole. All right, I promise we are almost over. 2 more things. Define directly proportional. This is how that would look. Y, the symbol means proportional to x. K is a constant, so y is directly proportional to x in this equation, which means the ratio between the variables stays constant, stays about the same. So as one increases, the other also increases. Or if one decreases, then the other will decrease as well. And you can see that here in our graph. As grams increase, so do our centimeters cubed, our volume. And lastly, inversely proportional. Y is proportional to 1 divided by x, which could be written as our constant, what we're trying to find, equals y times x. This means these two are inversely proportional. As y increases, x decreases. Sorry, I almost said increases. And then as x increases, y would decrease. And you can see that from our graph here. As our y decreases, x increases. All right, practice these for me by doing numbers 1 through 9 from our section assessment, which is found on page 55. And we will go over these in class and answer any questions you have. All right, thanks.